here to hear for the second time the results of the DNA that were presented previously by Giuseppe Baldacchini, but I will try to tell something more, just to don't annoy too much the audience. The outline of the talk, there are several points, so I have to run actually. The first point is some prehistory of shroud-like linear coloration by radiation. And of course, is one of the most nominated scientists in this conference is John Jackson. And I start from him. And in this paper, March 1990, he wrote a paper where it's written, UV radiation is suitable to obtain a shroud-like coloration for several reasons. And immediately after, Ray Roger replied that actually he was not convinced at all of the hypothesis of John Jackson and wrote some very interesting sentences. Experiments, that means something he has done. Experiments we did with pulsed ultraviolet laser on linen resulted in ablation, destructive shock waves. Samples often were converted into a little amorphous powder and gas. The surface of a shroud does not show the effects of radiation. The proposal of John Jackson is in March 19, the reply of Rogers is 91, and Rogers worked at the Los Alamos National Laboratory, LAN, and he used an excimer laser, because at that time it was the only laser emitting UV light. Now you have quite a larger choice. And by chance, in 1991, I was in Los Alamos National Laboratory as a visiting scientist. And at that time, I never heard about the shroud. And even I never met Ray Rogers. But this is very useful to me because Roger failed the attempt to color linen by using excimer laser. Because at that time, the excimer laser laboratory in Los Alamos National Laboratories there were only long pulse width excimer laser. And we will see later that the pulse duration is the main parameter to obtain a shroud-like coloration. Actually, as mentioned before by Giuseppe, we started our irradiation. We were not aware of the failure of Ray Rogers. We started with the same laser. He used almost the same characteristics, and we failed too. We didn't obtain any coloration using 120 nanoseconds. Short, not enough. So to opposite view, what is the synthesis? Correctly, Jackson replied to Rogers, mentioning the fact that a single experiment cannot tell you the truth. A single experiment means you tried one working point, but really you cannot discard the entire category of radiation on the basis of one experiment. And he was right. So we make a jump, 2002, where Testore et al., published in the Autex Research Journal, showed some experiments of shroud-like coloration, attempt of shroud-like coloration, using electron beams and CO2 laser, which emit in the far infrared at 10.6 micrometer. Just to understand, 10.6 micrometer is the wavelength emitted by a wall at room temperature. So we are in the infrared, really far infrared. And the results were terrible. You see here, fiber, these are electron microscope image of the fiber were burnt, destroyed, anything like something that looks like the shroud fibers. So we followed, at a given time in 2005, we followed the advice of John Jackson, and the reason is that UV light, not infrared, but UV light break chemical bonds without inducing a significant heating. We are talking about photochemical reaction. Moreover, linen and actually almost all materials have more absorptivity, which increases with decreasing the radiation wavelength. The smaller the wavelength, the thinner the material necessary to absorb the radiation. That means a shallow coloration. So we have chosen ultraviolet radiation as an acting at distance mechanism to obtain thin coloration depth, contactless action, and low temperature coloration process. There are some studies in the 70s, very old, because the problem with cellulose was not the linen, the most common problem. The most common problem with cellulose was the yellowing of books. Ancient books, you know, the page of ancient books become yellow after several years or several decades. The cellulose of the paper of the books is the same cellulose on the linen, exactly the same composition. So the first question we ask ourselves is okay, we will try UV light, but what's about the linen? We cannot use at least 600 or 700 years old linen. We must use modern linen. But fortunately, this is a result of Gilbert and the Sturp measurement, Shroud Turin Research Project measurement, of the reflectance of the Shroud of Turin as a function of the wavelength. And we made the same measurement with our linen, modern linen. And we see the dashed line is our linen, modern linen. And we see that around the green and yellow, our linen reflects a little less. But the most important is that at the wavelength we have used, or around 200 nanometer and around 300 nanometer, the reflectance is exactly the same, modern linen or shroud. And this is the most important properties. So this is just a frame of the two lasers we have used. On the right is the wrong laser. This is like the laser that were used in 1991 in Los Alamos laboratories. On the left is the good laser, is the short pulse width laser. This is an oscilloscope trace of the pulse, of the laser pulse. You see the half width, half maximum is about 20 nanoseconds, even less. This is a photograph of the fluorescence, blue fluorescence during irradiation. I remind you, ultraviolet light is invisible. We cannot see the laser pulse arriving. First, because it's very short. Second, because it's a wavelength that we cannot appreciate. But after the laser arrives on the linen reacts, reflecting blue light. And so in this way, we know where the laser is going on. Here, there should be a movie that should show basically the setup. The linen is on a wood frame, and probably if you switch off the light, you can see something better. And the laser fires at a given repetition rate to obtain finally the coloration. Here is a plot of laser intensity as a function of the pulse duration. And you see why we didn't obtain good results with 120 nanosecond pulse width, pulse duration. Because we are out of the coloration region, which is quite narrow. This blue region is the latent coloration. As I told this morning, latent coloration means a coloration which becomes visible only after aging of the linen, after irradiation, which did not create an image just after the irradiation at the moment. And finally, This is the below threshold area. I put a rectangular frame here, which is, oh, sorry. Oh, mamma mia. Okay. This is a red frame which may help your eye to recognize where is the laser, the yellowing of the laser, because the laser coloration is very faint. That is one of the characteristics of the shroud coloration. But after I take off the frame, you can still recognize that is just a little bit yellow, more yellow than the raw. This is a photograph of a piece of a thread, and you can see here the detail of the single fibril that are yellowed. And on the left, you see there is a white region, not colored region, close to the colored region, because here this part of the thread was covered by the other thread in the textile. Here is a depth of coloration shown by Giuseppe. I can jump. We obtained, in one case, a fibril, which the vacuum ultraviolet light did not color the secondary cell wall, that is what is inside. A single fiber is made by a very thin layer called primary cell wall, very thin. 1/5 of thousandth of millimeter, very thin. Inside this pellicle, there is the secondary cell wall, sometimes called lumen. And one of the properties of the shroud is that the coloration is limited to the primary cell wall. Well, zooming in this broken by chance fibril, we see there is a yellowish coloration, no coloration apparently inside the secondary cell wall, and again, coloration. But the most interesting thing is about 3 shreds of the primary cell wall, here, here, and here. Of course, only this one is in focus, because the depth of the microscope doesn't allow you to put it all at focus. And you will see here, these shreds are yellow. So our conclusion is that we are really coloring the outer primary cell wall. That is 200 nanometer thick. That is 1/5 of thousandth of millimeter. And this is quite an interesting result about the half-tone effect. We occasionally obtained the half-tone effect. You see here some fibers close to uncolored fibers, colored fibers close to uncolored, exactly what happens in the shroud image. And why we obtained this result? Just by chance, because the laser is not a perfect tool. The spatial shape of the laser intensity is not flat. It has some noise, and this noise, if you put correctly the value of the intensity, in some point you are above threshold, that is sufficient to color. In some point you are below threshold, not sufficient to color. And in this way we can obtain colored fiber close to not colored fiber. Latent images, I mentioned you the meaning of latent images. We have colored linen, and the red rectangle show you the spot, the sides of the laser. this part was heated to accelerate the aging. And it appears the spot of the laser, the yellowing of the laser. The other part, which is not heated, that is not aged, doesn't show the spot of the laser. So it's something like radiation changed something in the structure, in the molecular structure of the cellulose, but this change is not sufficient to color it. But it is a preparation for coloration after dehydration of the cellulose. It's something like when, from a technical point of view, when you have OH atoms, oxygen, hydrogen atoms, that escape during dehydration. In this way, the remaining cellulose molecules bind in such a way to create the chromophore. We will see now what's the meaning of chromophore. This is the chemical structure of the cellulose that was shown even this morning by Carlos. And we have found two different paths that finally create the double bonds CO and CC. These are the chromophore. What is the chromophore? Is the molecule, the atoms bonded that absorb visible light, illuminating light, and reflects yellow light. This is the chromophore. Is responsible for the yellowish coloration of the linen after laser irradiation. And we are actually quite proud of these results because this is just a slide. This slide means 1 year of work to understand which kind of path is reasonable and possible. What's about the requirement of Sturp that the process that created the image on the shroud is a low temperature process? That is, it cannot be obtained by heated statue or rubbing on a statue hot. We have made, thanks to infrared camera given by Giulio Fanti, we made a photograph of the linen, you see here, in the infrared during laser irradiation. And when using 308 nanometers, we see that inside the laser spot, the temperature rises to 34 degrees. I'm sorry, I don't know the Fahrenheit. I don't know. I cannot translate it. I cannot translate it in your unit. But say 34 degrees is something like a quite hot day, starting from 21, which is the temperature of the not irradiated linen. But when we use a vacuum ultraviolet, what creates a yellow, you see the temperature rises only 3 degrees more than the room temperature. This is a very cold mechanism, very cold mechanism. It's not thermal at all. Of course, we did coloration of, say, 1 or 2 square centimeters, but we made also something more. This is a laser that is firing now. There is no audio, but you could should hear the laser firing. The laser beam is reflected, meet the lens here, and it is focused, the lens here, and it is focused on the linen. And you will see here the blue fluorescence of the laser spot. And you see, during the laser spot is fixed, we move the linen. We are using the laser as a brush, but we don't move the brush. It's the linen which moves. It's the same. It's the same. I'm a painter which don't like to make the fabric. I'm tired, so I prefer to move the paper instead of the brush. Why is going on a given point? Because it is controlled by a dedicated software that asks to stop in points able to recreate the face of the shroud according to the logo of the 2010 exhibition. And okay, we have to close this. Maybe here is, I don't know, is waiting for. I cannot get on. It's waiting for something. Anyway, in the next slides, I will show you more in detail the phase we have obtained and its characteristics that are quite interesting. Okay. This is the good one. Oh.
It's the one you want.
Ah. I have to go there. Here.
Yeah, it's not one you think. There's another.
Too many things switch long. Okay. Oh, this is the phase of the man of the shroud we obtained. Can you see something? Hand up. Nobody see anything? Me too. I cannot see anything. This is a photograph taken in sunshine. So the image is a low contrast image. Can you imagine? The shroud is a low contrast image. If you put the shroud on full sunshine, you can hardly see something. But if I go in shadow, well, not very clear, but I can see some yellowing. Can you see it? Maybe switching off the light, you will see it. And finally, if I make the negative of this piece of linen, I obtain this. That is a pseudo-negative, it's actually like the shroud. And you can recognize the single laser spot that putting together recreate a shroud-like face. This is just maybe 50 square centimeter, even less than 50 square centimeter a piece of linen, and we needed, let's say, 20 minutes to finish this work. So if you can do it at the full size, you need several days. Our results generated quite a widespread attention in the media worldwide, from National Geographic to many other press and web sites, and you see it's a lot. It's a lot. But finally, what they did, what they told to laymen. some statements I extracted from the press. Italian team suggests the shroud is authentic. It's not true. We have colored a piece of linen. We are not talking about authenticity. It's different. We must pay attention. We must be rigorous. Enea shows the body image on shroud was created by flash. It's not true. We have created a shroud-like image. We cannot be sure that the shroud was created in the same way, of course, but more in general, and this is maybe a topic for the next discussion, Russ, this is an important topic. Science cannot prove anything. Science can disprove something. It is important to understand this point. I mean, if I try to color the linen with a laser, UV laser, and I obtain no results at all, and my experiment is well done, that means science can say, okay, UV is not the right way. You cannot do a shroud-like image by UV, if. If, on the contrary, like in our case, we obtain quite good and interesting results by UV, science cannot say, okay, you find a way. No, sorry. This is one of the possible ways to obtain a shroud-like image. Is a teeny boundary, is a thin boundary between what I can say and what I cannot say. Science disproves, science cannot prove. It's important. More, Italian scientists say science cannot explain the image of the shroud. That's true, absolutely true, because all the attempts till today failed to reproduce 100% of the microscopic image, not macroscopic, microscopic image characteristics. Finally, Enea demonstrates the shroud is not a medieval fake. Why? I am coloring a piece of linen. Nothing to do with the radiocarbon dating. So all these sentences help us to understand that it's very easy to be misunderstood when you talk of something which has a so big impact with press and people. Here there is a short movie, but unfortunately we were not able, with the help of our friend, to make the movie working. But it was very nice because it was 3 minutes that you can find it in YouTube. YouTube, you look for vortex and write 34,000 billion watts. It was a Catholic Herald that made a YouTube movie in which the presenter said, okay, at Enea they obtained an unbelievable result, is that to reproduce the wool shroud image, you need 34,000 billion watts. 34,000 billion watts is a lot, and so on. It's interesting to, yeah, this is the movie that does not exist. 34,000 billion watts is impressive, but is a fraction. Let's go back to basics. A fraction A divided B, independent of how much is big A, if B is small, the fraction is very high. So in our case, 17 joule energy divided by 0.000001 second, that is the duration of the laser pulse, results in 1.7 billion watts. That is quite a considerable power, but it is peak power, not average power. When you have a power plant, it generates average power, not peak power. So we are talking of something little different. And how comes out 34,000 billion watts? Because this peak power, 1.7 billion watts, was delivered to only 1 square centimeter surface of the linen. A surface of the human skin is about 2 square meters. 2 square meters means 20,000 square centimeters. So I must multiply this 1.7 billion watts times 20,000, and the final result is 34,000 billion watts. That is, again, impressive number, but we have to understand it is peak power, not average power. And many thanks to Joe Jackson that several years ago flagged me that it may be misunderstood at this point. Well, we are almost at the end. Are we looking for a scientific search for God? Ross, how do you think? Philip Ball, Nature Online, January 2005. Scientific study of Shroud of Turin is like a microcosm of scientific search of God. It does more to inflame any debate than settle it. It is simply not known how the ghostly image of a serene bearded man was made. It's still true. It was 2005. Still true? Well, I think, yes, still true. You see here, this is a list of the main attempts of image reproduction. To today, say. And the most interesting are the last three attempts, Garlaschelli 2010, which is absolutely unlike at the fiber level. The attempts, experiments by Fanti and co-workers on corona discharge that work only with a conductive dummy. And the most important, the image is on the outer side, it's not on the facing side. That is quite a big problem. And our experiment at Enea, where life-size image is beyond today technology. So we are still the problem of Philip Ball. We don't know how, we don't have idea how the image was formed if we stay on the physics. If we stay on science fiction can tell whatever you like. Conclusion. We have shown the ability of ultra-short UV and VUV radiation to reproduce many peculiar aspects of the microscopic complexity of Turin Shroud image. Wow. The UV radiation works only in a very narrow range. It's difficult to find the good point, the good working point. It's very difficult. You change 5%, one of the parameter, coloration disappears. It's very critical. The most important parameter is the pulse width, which must be shorter than 50 billionth of second, not 100 as said by Giuseppe before, because Rogers used 50 nanosecond pulse duration, and he failed. Then, the permanent effect is a threshold effect. That is, you have to go above a given number of intensity. Below that number, you don't obtain coloration. But there is a narrow strip of energy in which you can obtain latent coloration. That is a coloration that does not appear immediately. We have shown that we have triggered photochemical cold reaction because the temperature of the linen irradiated rises only to a few degrees centigrade. The hue color depends on the wavelength of radiation and on the number of pulses. But in any case, the color contrast increases with the number of laser pulses. And this is very important because it allowed us to an accurate control of the color of the linen till to obtain the right one. The different color, this is very technical, different color depends on the photolytic degradation of the cellulose, finally to create the double bands that are the CC and CO that are the chromophore. We observed an irradiated fiber whose coloration was confined in the primary cell wall, exactly like in the case of the Shroud. Latent coloration, I mentioned before. What I didn't tell before is that the latent coloration is very interesting for historians because they are attracted by the possibility that the Shroud image may have developed over time, years, from the moment the process of latent coloration acted. So that means if the Shroud is authentic, it's possible that Peter and John that went to the sepulchre could not see the image because it was latent coloration, just speculation. I didn't show it, but we obtained also a reduced fluorescence, that is not a zero fluorescence, a reduced fluorescence induced by UV and VUV similar to those to those reduced fluorescence that have been measured by the Shroud Turin research project. I've obtained, and it's very important, we have obtained half-tone effect. Half-tone effect is a very puzzling property of the Shroud of Turin image. I think it's very difficult to obtain it. There is indirect consequences. I didn't show the photograph, no time, but we have observed some defects induced by UV radiation. In other words, the UV radiation generates an accelerated aging of the linen. This is another very important property. When considering the highly unconventional hypothesis of the shroud collapsing into a radiating body proposed by Jackson, UV light is compatible with both shedding correlation with cloth body distance and the absence of side image. Why? Because vacuum ultraviolet radiation are strongly absorbed by air. This is very important. So if the photons make a travel little longer, it is absorbed, and maybe its intensity when it arrives on the cloth is not sufficient to color. This may explain why we don't take lateral images. However, when obtaining shroud-like coloration by UV radiation, it does not mean the body image of the shroud was generated by flash of UV light. From a scientific point of view, it means that it is not impossible that UV radiation may have played a role in the image formation. I repeat, science disproves, cannot prove.
5 minutes behind.
The final question, what is a shroud? We could tell you what it isn't. Not a painting, not a photograph, not a sculpture, not a wrapping, but we don't know mechanism that can make an image with the same chemical and physical properties as the image on the shroud. And most important, people often ask me, does this prove resurrection? The answer to fate is not going to be on that piece of cloth, but more likely in the eye and ears of those who look upon it. These are wise words that I completely approve. Thank you very much for your attention.
Thank you, Paolo. That was fantastic. And as you know, I use your work in my presentation. So, and I'm glad you had Barry up here at the end because he can't be here. He's going off to England. And I just want to know if Doc Brown was up to something when he knew that it took 1.21 gigawatts of power to go into that flux capacitor. You think that? I don't know.
Is it on?
Just thinking that. Our next speaker is from